So this week we have learned about hypothesis testing in case you have two samples, and then how do you find out how do you test the claim about the difference of the two population means, or if they are paired, then how do you do the testing. So under different situations we have looked for difference of means, then ratio of variances. Likewise we also did for the difference of the two proportions. So we studied the theory part of that, and in addition we looked at chi-square test of independence and chi-square goodness of fit test. So now we are going to look at their corresponding codes, how we can do them in Python. So first of all, we will look for the test for the difference of the two means, such that the two populations, the samples that have been taken, they are independent and they have equal variances. So let me just mention that as a comment. Test for mu1 minus mu2 in case of independent samples and equal variances. So first of all, as you know, we are going to import the necessary libraries. So here we need NumPy. We also need SciPys. From SciPy we can just import stats, because we are going to work with lot of statistical functions over here. We need to calculate your critical values for the t distribution, so here we need it. Now let us also set the random seed. So np.random.seed, we know the function of this just to ensure reproducibility, so we mentioned this. It is also coming from your NumPy library. Now let us mention the means and the variance for the two populations, because they are coming from normal. So let us denote like mean 1 and STD1. These are, suppose mean 1 is 10 and standard deviation is 2. So basically we are taking the sample from normal distribution with mean 10 and variance 4. Likewise for the second one also you can have. So here we are taking mean as 8 and standard deviation as 2. So which basically means that we are taking samples from normal populations with equal variances, that is 4. Okay. So now we are going to draw samples from these using np.random.normal. So we need to draw a sample. Okay, so here mean would be this STD1 and the sample size. So let me also mention the sample size over here. Let that be sample size be suppose 20. Okay, because we are drawing from normal, so sample size of 20 is also applicable here. Obviously you can increase it and look at the pattern. So here you can see that what we have written over here, basically we are generating a random sample from normal distribution with mean 1 and variance. This is standard deviation. So basically we use np.random.normal, which is a function used for drawing random samples from your normal distribution. So we have, I believe, used it earlier also. So similarly you want for the second sample also. So here the difference would be coming with just these different means and standard deviations. Okay. So instead of writing STD1 and STD2, you could have just written STD below, and separately we could have mentioned as 2. So in these two places it would have been STD only. Okay. So that is also another way of doing it. So right now we are just following this pattern. Now let us set the hypothesized mean value, difference of the mean value. So let that d0 be 0. So this is your hypothesized mean difference, right? Because you want to check whether the difference between the two means is less than equal to d0 versus whether it is greater than d0 in case of right tail test. And in different tests we will have different hypothesis, but this d naught, we can keep it as 0. So now let us define the function for the test. Okay, so for this we write df, which is used for writing the function. So we are defining, this is the name of the function, right-tailed underscore test, and these are the inputs. So sample 1, sample 2, d naught, and alpha as 0.05. So these are the input to your function. Sorry. Okay, here n1, n2 is the length of sample 1 and length of sample 2. Okay, so here you can see that these are the parameters of the function. So we are going to compare these two samples. Okay, and this is the hypothesized, d naught is the hypothesized difference between the means, right? And alpha, obviously you know that this is the level of significance, so we are taking it as 0.05 in this case. So degree of freedom, if you remember, it is n1 plus n2 minus 2, right? So DOF can be n1 plus n2 minus 2, and then since we have equal variances, it means we are going to deal with your pooled standard deviation. So let me write the command for that. So np dot square root, because it is not the variance, so I am just writing the standard deviation, so I am mentioning square root function. So np dot square root, so here it would be n1 minus 1 into s1 square, right? The sample variance of the first sample. So np dot var, and here it would be sample 1 comma ddf as 1, because we know that we have to deal with the sample variance. Okay, next same thing would be there for n2 minus 1, because if you know the formula, then you can write it easily. So here it would be n2 minus 1, and we have to multiply it with the sample variance of the second one. Okay, and finally you have to divide it by DDOF, that is the total degrees of freedom, sorry, DOF, n1 plus n2 minus 2, and one more bracket would be here. So finally it means that we need one more bracket at this end. Okay, so the formula is this, if you just forget the square root, then we have n1 minus 1, right, into the sample variance of the first one plus n2 minus 1 into the sample variance of the second one, and divided by the total degrees of freedom, that is n1 plus n2 minus 2. After defining this, we can also mention the test statistic. Okay, so it is in the numerator, what do you have? You have x1 bar minus x2 bar minus d naught, right? That is the hypothesized value, and since d naught over here is 0, you can skip it, but if you want, you can write in the formula also. So let me just write it. np dot mean for this first sample, okay, minus np dot mean of the second sample, okay, minus d naught, right? So x1 bar minus x2 bar minus d naught whole divided by s pooled, because you in the denominator you have that sp, s suffix p, right? So s pooled into np.sqrt 1 over n1 plus 1 over n2. Okay, so we just written the formula only, right? Nothing else. So it is x1 bar minus x2 bar minus d naught in the numerator, and the denominator you have the pooled standard deviation multiplied by the square root of 1 over n1 plus 1 over n2. Okay, so let us check the number of brackets if it is correct. Yeah. Okay, now you can find the critical value. So critical value, that is would be calculated using stats dot t dot ppf. So 1 minus alpha comma DOF, right? So critical value, we know that this percent point function is used for this, and which is the inverse of your CDF basically, right? So if we are mentioning this over here, it means that it is going to find the t value that corresponds to this particular cumulative probability. So if alpha we have taken as 0.05, so it means that 1 minus alpha would be 0.95, and we are basically looking for a t value in the t distribution such that 95% of the values are lying to the left of it, right? So as I told you that PPF works and looks at the data points from the left end. Okay, so in the theory you might have seen that we are comparing the t star value with the critical value at t, and suffix alpha is there. So since alpha is 0.05 in this case, so and alpha is the region that is to the right of the critical value. However, in Python, when you are using PPF function, so it means that we are looking at what is left or what is to the left of that particular value, critical value. So that is why we write 1 minus alpha over here. So I discussed it in the last lecture also. So return, what it will give you? It will give you the t star value, and it will also compare your t star with the critical value. Okay, this is what we want. So this is for your right tail test, right? Because in right tail we do in this way, t star, if t star, we are going to reject the null hypothesis if t star is greater than your t alpha. So in the same way we can also define your left tail test. So let me mention that. Define left tailed test. So again we would have sample 1, sample 2, d naught, and alpha as 0.05, and here we want t star and the result of the right tail test. So I will explain you why am I writing like this. So basically here what we are doing, we are calling this previous function, that is the right tail test, but we are reversing the role of sample 1 and sample 2, because this effectively turns the right tail test into the left tail test, because you are now testing if the sample mean of the second one is significantly greater than your first sample mean, right? Because in this case what do you check? The alternative in left tail test is basically that mu1 minus mu2 is less than d naught. So here if d naught is 0, it means that mu1 is less than equal to mu2. So the role of the sample means we are basically reversing that, and we want it to return minus of this value and the result. Okay, so negative of this calculated test statistic would be obtained, because here the negation we are doing because the direction of the test is reversed, like from right tail to left tailed. So this is one way of doing it. Likewise, you can also define your two-tailed test. Again, same arguments would be there. So if I just copy from here and so sample 1, sample 2, D naught, alpha will be 0.05, N1, N2 will be there, degree of freedom, S pooled will be there, T star value, critical value here in this case it would be 1 minus alpha by 2. Okay, and we are going to return, return T star and NP. So we look at the absolute value of this and we compare it with the critical value. Okay, so again alpha is 0.05, so it means alpha by 2 will be 0.025. So 1 minus alpha by 2 will be 0.975. So we are looking for a t value in the t distribution such that 97.5% of the values lie to the left of it. Because in theory, what do you have? You are going to reject the null hypothesis if absolute value of this t star, that is a test statistic you have calculated, is greater than equal to t alpha by 2. Right? So alpha by 2 means that to the right of it you will have alpha by 2 region. So it is same as saying that 1 minus alpha by 2 would be to the left of it. So we have defined these functions. Now we are going to do the final testing. So let me mention for the right tail test. So here we need the T star. And the result, we are calling this function now right tail test, sample 1, sample 2 and D naught. And it would print, sorry, here is an extra bracket, probably that is why it's coming. Okay, finally it is going to print right tailed test. Right tail test statistic is T star and reject H naught, whatever is the result that we have obtained. Okay, so the right tail test statistic, that is critical value that we have found, is 3.590 and reject H naught, which is true over here. So it is giving you a Boolean result, whether to indicate that whether you are going to reject the null hypothesis or not. So reject H naught is true, it means you are going to reject the null hypothesis, that the difference between the two means is, so mu1 is greater than mu2. Okay, so this is for your right tail test. Likewise, you can also compute for other tests. So let me reuse this. So case 2 will be for your left tail test. Okay, so T star, and here we are going to call the left tail test function. Left tail test statistic. So we need the T star and we need this region. So left tail test statistic is this, and you are again rejecting this null hypothesis. Okay, so that is false. So reject H naught is false It means that you failed to reject the null hypothesis. Likewise, if you look for the two-tailed test, so this is your third case. Okay, so here we are going to call your two-tailed test. So obviously the test statistic remains the same in all the three cases, right? If you remember from the slides also, the difference comes when you are comparing the critical value and your test statistic. So in different cases, so here it is T alpha, other places it is minus T alpha, and or you can also have T alpha by 2. So you can see that what are the results. So this is how you can write the code in Python when you want to test whether the difference of the two means is less than some hypothesized mean difference. So here if I am writing d naught as 1, if I change this d naught value, likewise everywhere the calculation would change. So this was your first situation, the test for the difference of the two means, independent sample and equal variances. We know that the second test we considered in your theory was that you do not have equal variances. So let me just write unequal variances, which means that we are going to work with your Wells t-test, right? So you will be importing your numpy, import numpy as np, and from scipy dot stats, or maybe just from scipy you just import stats. That will cover everything. So now let us consider that sample 1 that you have is generated from np dot random dot normal. So we are taking mean as 2, variance as mean as 5, variance as 2, and sample size 20. Likewise, for the second sample, we are taking np dot random dot normal 8, 4, and 20. So d naught is 0 in this case. So now we will first calculate the degrees of freedom, because if you can recollect, degrees of freedom was a typical thing. There is a long formula for that. So let me first calculate the degrees of freedom. So n1, n2, let me mention this as the sample size, sample 1, and length of sample 2. Okay, so the degree of freedom in this case, so what is the formula for the degree of freedom? In the numerator you have s1 square over n1 plus s2 square over n2 whole square, and you divide by s1 square over n1 whole square n1 minus 1 plus s2 square over n2 whole square divided by n2 minus 1. So we just have to enter this entire formula over here. So let me just mention np dot variance of the first sample. Okay, this divided by n1. Okay, so here there is one more bracket. Yeah, so same thing. We need for the second sample as well, and it will be divided by n2, and this whole raised to the power 2. Okay, now you have to divide it by, again, np dot var thing. So this is sample variance s1 square over this whole raised to the power 2, and this whole will be divided by your n1 minus 1 also. So it would be sample 2, it would be N2, so this bracket over here, so we want S1 square over N1 whole raised power 2, so this is ending fine. So this, and here again, so this one will be S2 square over N2. So let me just run this and see if it's working fine. Yeah, so number of the brackets are correct. Good. Okay, now suppose you want to conduct a right tail test for this. So as I have done earlier, you can do for other tests as well. So because of the time constraint, I will just focus on one of the tests and show you. So in this one, let me take the right tail test. Because the steps are more or less same only, right? So define right tailed test as sample 1, sample 2, D0 and alpha 0.05. Okay, now you calculate your test statistic. So again, in the numerator, what do you have? You have NP dot mean, that is first sample mean, sample 1 minus NP dot mean, sample 2 minus D0, denominator would be NP dot square root. So NP dot where, so you have sample variance S1 square NP dot so here we are going to divide it by N1 because that is the sample size of the first one. Plus same thing for your second one. Since this entire thing is in square root, okay, so I will add over here. So this one would be sample 2 and here it will be divided by N2. Fine. So now your T star would be numerator divided by denominator. Critical value would be again stats dot T dot ppf. So 1 minus alpha, degrees of freedom that we have already calculated, and it is going to return T star value. Okay, and it will check if T star is greater than your critical value. Yeah, so for this, let us finally get, we want T star and we want the result equal to right tail test here. So maybe I could mention unequal so that you can differentiate. So unequal, this is the function that we are calling, and it has to work with sample 1, sample 2 and your D0. sorry, sample 2. So if you want the T star value, so let me just print the result. What is the result is false, that you are not going to reject the null hypothesis in this case for the right tail test. Okay, and what is the test statistic that we have obtained here? If you want to give a proper print command as we have done earlier, you can do it. So T star value comes out as like this. So maybe the degrees of freedom I can cross check, 32.87. So with these values you maybe cross check this, because here let us hope that these brackets are fine. So you can cross check this value once. So this is how you do for the unequal variances. So this is for your right tail. Likewise you can write for left tail as we have done just now in the previous situation, and you can again do it for the two tail test also. Now we are going to work with when data is paired. All right, so that was our third case. So we are going to import numpy as np, and from scipy import stats. Okay, so data 1, these things we can take same. Okay, so maybe I could use a different name, data 1. So we are basically drawing two samples from normal distribution with the given mean and variances. D0 is 0. Now we have to suppose do the right tail test again. So we have to first define this function. This is the name of the function, right tail test, and these are the arguments. So here right tailed paired test. Okay, so here it would be data 1, data 2, D0, and alpha as 0.05. Okay, and n would be the length of your data set. Because it is paired, n1 and n2 is going to be same anyhow. Now we can calculate the differences, because here if this is your xi's and these are your yi's, so you calculate the corresponding differences, that is di's. So xi minus yi. So for that, let me mention differences as data 1 minus data 2. Okay, then you calculate d bar sd, right? So d bar would be the mean of those differences. So let me write mean difference would be np dot mean of these differences, and sd would be np dot std okay. Now you can calculate your t star value. So mean underscore differences minus d0 sd underscore differences divided by square root of n, right? So np dot sqrt of this n. So this is your t star value, test statistic, because it is d bar minus d0 whole divided by sd over root n. Then the critical value would be calculated. Critical value here would be calculated using this stats dot t dot ppf percent point function again. So 1 minus alpha n minus 1, and it would return the t star value and the result, or you could say it checks t star is greater than the critical value or not. Okay, once you have defined this function, now we can call it. Finally, you will have t star value, and the result would be this function that we have defined here. We are calling it, we want the result of this and the t star value. Right, so let us print what is t star for us. It is minus 1.73, and your result is basically false in this case. If you want, you can also see the critical value, so to which we are comparing. So this is how you can do the hypothesis testing when the data is paired. So likewise you can do for left tail test also. So same steps would be there, you can define in the same way. Just the difference here that the critical value here would change. Okay, minus of that would come, and likewise for the two tail test you would compare the absolute values with the t alpha by 2, and you can get the results.